So this was all about the linear regression. Now let's have a discussion on the logistic regression. So the aim of this lecture is to understand that when and why do we need to use logistic regression. What are the cases where the linear regression fails, or what are the cases where we cannot use linear regression and we have to use in logistic regression. And we will see two cases here of logistic regression. We will see a binary logistic regression case, and we will also see a multinomial logistic regression case. Then we will also study some theory behind logistic regression. We will see that how we can assess our logistic regression model, how can we assess the prediction which are being made by logistic regression, and what are the things that could go wrong in logistic regression. And then we will also see that how we can interpret the results obtained from logistic regression. So the first question is that when and why we should use logistic regression, right? Because now we also have linear regression and we also have logistic regression, so it is very necessary to see or understand that why we cannot use linear regression and why we need to switch towards the logistic regression. So the one thing is that if we want to predict an outcome variable that is categorical from one or more categorical or continuous predictive variables, right? So the first thing which we need to check is that if we want to predict an outcome variable that is categorical or not. The number two thing is that we can use, because having a categorical outcome variable violates the assumption of linearity in normal regression, because in linear regression we assume that there should be a linear relationship between the data samples. So if there is this assumption is being violated and there is non-linearity in the data, then it is not possible for us to solve that problem with simple linear regression. Also, no assumptions about the distributions of the predictor variable. So these 4 points also indicates that what are the conditions after which we need to switch towards the logistic regression. Number two thing is that the predictors do not have to be normally distributed. If the predictors are not normally distributed, then we can also say that we cannot use linear regression. Logistic regression does not make any assumptions of normality, linearity, and homogeneity of variance for the independent variables. So all these conditions which were necessary to be satisfied in the case of linear regression, now we are not handling those. So in case of logistic regression, there is no assumption of normality or linearity in the independent variables. Because it does not impose these requirements, it is preferred to discriminant analysis when the data does not satisfy these assumptions. So whenever we have a problem in which our data is not fulfilling the assumption of normality or linearity and the homogeneity of variance, then we can always try to solve this with logistic regression, because in that case our linear regression will not be helpful. Okay, so now let's see that what is logistic regression. Logistic regression is used to analyze relationships between a dichotomous dependent variable and continue or dichotomous independent variables, right? So normally we use SPSS in order to do the binary or multinomial logistic regression. So the logistic regression combines the independent variables to estimate the probability that a particular event will occur. That is, a subject will be a member of one of the groups defined by the dichotomous dependent variable. So if we go a little bit in more detail, let's represent these things with our equation. So let's first discuss a simpler case which is a case of one predictor. So in case of one predictor, we can represent P of y with this equation, right? So in this equation, the outcome is the when we predict the probability of the outcome occurring, right? So you can see that there are two variables b naught and b1 involved in this equation, and this can be thought of in much the same way as we use this in our previous simple linear regression equation. So you can consider these variables to be behaving in the same way as they were behaving before. Now note that the normal regression equation forms part of the logistic regression equation. Okay, so this was the case when we had only one predictor variable, right? So we now know that in case of logistic regression we can have more than one predictor, because now the data is categorical data, right? So if we have more than one predictor or several predictor, then we can generalize our equation with this by having an addition of more variables. Now the outcome will be still the prediction of the probability of the outcome occurring, but there will be the differences, and you will see that the differences will be that the multiple regression equations forms part of the logistic regression equation, right? So in case of several predictor, you can have multiple regression equations and they will make part of the whole logistic regression equation. This part of the equation expands to accommodate additional predictors. So we are increasing our equation, and this increase is basically to accommodate the additional predictors, because this equation is basically representing logistic regression for multiple predictors. So if we generalize our logistic regression equation, we can represent it with this equation, and you will see that in this equation we have used alpha and beta. So alpha in this equation represents the overall disease risk, and the beta 1 represents the fraction by which the disease risk is altered by a unit change in x1, and beta 2 is the fraction by which the disease risk is altered by a unit change in x2. So we are having a beta variable which is changing with the x1 and x2, right? So depending upon how much change we have in our x1, x2 or x3 variables, on the basis of that we have a change by a fraction in beta 1 and beta 2 and so on. So now in order to measure the probability of the outcome, we can use our classical probabilistical or theoretical knowledge, the statistical knowledge. So we know from our statistical background that the probability of the outcome is measured by the odds of occurrence of an event, right? So if the probability for occurring an event is represented by P, then the probability that that specific event will not occur is represented by 1 minus P, right? So in this way we can represent the odds of success with this equation, which is P over 1 minus P, right? So this equation is basically representing the odds of success, where P is the probability of occurring an event and 1 minus P is the probability that the certain event will not occur.